Today we are going to learn about mastering adaptive optimization in PyTorch. We'll explore the use of Adam and RMSprop optimizers, focusing on their implementation and selection for various neural networks, enhancing your deep learning model training skills. Welcome to our video on mastering adaptive optimization in PyTorch. Adaptive optimizers are a class of algorithms that adjust learning rates during training to improve convergence rates. They are particularly useful in deep learning, where the landscape of the loss function can be complex and challenging to navigate. In this video, we'll focus on two popular adaptive optimizers, Adam and RMSprop. These optimizers have become crucial in efficiently training deep learning models by dynamically adjusting learning rates based on the characteristics of the data and the model. Understanding and implementing these optimizers can significantly enhance the performance of your neural networks. Let's dive into the world of adaptive optimization and see how these algorithms work and why they are essential in the modern deep learning toolkit. To better understand adaptive optimizers, let's compare them with their non-adaptive counterparts. Non-adaptive optimizers, like stochastic gradient descent, (SGD), use a constant learning rate throughout the training process. While this can be effective, it often requires careful tuning of the learning rate and might struggle with varying learning dynamics across different layers or data characteristics. In contrast, adaptive optimizers like Adam and RMSprop adjust the learning rates for each parameter individually and dynamically. This adjustment is based on previous gradients, allowing the optimizer to adapt to the training process's needs. This adaptability often leads to faster convergence and can handle larger datasets or complex models more effectively. Adaptive optimizers can also provide stability in training, reducing the likelihood of overshooting minima, a common issue with non-adaptive methods. When choosing between these optimizers, consider factors like your dataset size, model complexity, and the computational resources at your disposal. Adaptive optimizers are particularly beneficial for deep learning tasks, where their ability to handle non-stationary objectives and noisy gradients is crucial.
The Adam optimizer, short for adaptive moment estimation, has become one of the most widely used optimization algorithms in deep learning. Introduced by D.P. Kingma and J. Ba in 2014, Adam combines the best properties of the Ada-Grad and RMSprop algorithms to provide an optimization technique that works well across a wide range of problems. The core idea behind Adam is to maintain a moving average of the gradients and their squares, which helps in efficiently adapting the learning rate for each parameter. This adaptation allows for faster convergence and more robust training across different types of neural networks. One of Adam's key advantages is its ability to handle sparse gradients, making it particularly suitable for natural language processing tasks and other applications where data sparsity is common. Additionally, Adam's default parameter values often perform well out of the box, reducing the need for extensive hyperparameter tuning. However, it's essential to be aware of scenarios where Adam might not be the best choice, such as when extreme precision is required, or the model's parameters are highly correlated. Despite these considerations, Adam remains a powerful tool for most deep learning practitioners. RMSprop, or root mean square propagation, was developed to address the problem of non-stationary learning rates that can occur during training. Proposed by Geoffrey Hinton, RMSprop adjusts the learning rate based on the average of recent magnitudes of the gradients for the weights. This adjustment allows RMSprop to perform well in online and non-stationary settings, which are common in real-world deep learning applications. The algorithm works by dividing the learning rate for a weight by a running average of the magnitudes of recent gradients for that weight. This method helps to normalize the parameter updates, preventing them from becoming too large and ensuring more stable convergence. RMSprop is particularly useful in cases where the learning rate needs to adapt quickly to changes in the gradient direction, such as in reinforcement learning. However, like all optimizers, it requires tuning of its hyperparameters, such as the decay rate, to achieve optimal performance. Understanding how RMSprop handles learning rate decay and its implications on training stability can guide you in choosing the right optimizer for your specific needs. Learning rate schedules are a crucial component in the optimization process, providing a systematic way to adjust the learning rate during training. While adaptive optimizers inherently adjust learning rates based on gradient information, incorporating learning rate schedules can further enhance the training process. Common types of learning rate schedules include step decay, where the learning rate is reduced by a factor after a set number of epochs, exponential decay, which continuously decreases the learning rate at an exponential rate, and cosine annealing, which gradually reduces the learning rate following a cosine curve. Each of these schedules offers unique benefits and can be combined with adaptive optimizers to balance exploration of the loss landscape and convergence to a local minima. For instance, starting with a higher learning rate can enable faster exploration early on, while gradually reducing the rate can aid in fine-tuning and achieving more accurate convergence. Implementing learning rate schedules in PyTorch with adaptive optimizers involves using tools such as the torch.optim.lr_scheduler module, which provides a simple interface for integrating various scheduling strategies. By understanding and applying these schedules, you can achieve more efficient and effective training in your deep learning models. Implementing the Adam optimizer in PyTorch is straightforward, thanks to its user-friendly API. To get started, ensure that your PyTorch environment is set up and ready for development. Once you have your model and data prepared, you can create an instance of the Adam optimizer using torch.optim.atom. You'll need to pass in the model's parameters and can optionally specify hyperparameters such as the learning rate, beta 1, and beta 2. A typical setup might look like this: optimizer equals torch.optim.atom model.parameters, LR equals 0.001, betas equals 0.9, 0.999. It's important to monitor the training progress using tools like TensorBoard or custom logging, as this will help you identify and debug any issues that arise. Common problems might include learning rate being too high or low, leading to unstable training or slow convergence. By keeping an eye on metrics such as loss and accuracy, you can make informed adjustments to your optimizer settings. PyTorch's flexibility allows for easy experimentation and iteration, making it an ideal platform for implementing and refining your use of Adam in deep learning projects.
While adaptive optimizers like Adam and RMSprop offer significant advantages, they are not without potential pitfalls. One common issue is overfitting, which can occur if the learning rate is too aggressive, causing the model to memorize the training data rather than generalizing well to unseen data. To mitigate this, consider using techniques like dropout or early stopping. Another challenge is selecting the correct hyperparameters. While the default values for Adam often work well, they are not universally optimal. Experimentation and validation are key to finding the right balance. It's also crucial not to ignore weight decay, which can help regularize the learning process and prevent overfitting. Over-reliance on default settings can lead to suboptimal performance, so it's important to understand the underlying mechanics and be willing to adjust parameters as needed. By being aware of these pitfalls and proactively addressing them, you can harness the full potential of adaptive optimizers in your deep learning projects. To maximize the effectiveness of adaptive optimizers in deep learning, consider several best practices. First, invest time in hyperparameter tuning, as this can dramatically impact your model's performance. Use techniques such as grid search or random search to explore the parameter space and find optimal settings. Monitoring and adjusting learning rates is also crucial, even with adaptive optimizers. Starting with a well-chosen initial learning rate and adjusting it based on training feedback can lead to better outcomes. Combining optimizers with learning rate schedules, as discussed earlier, can provide additional control over the training process, helping balance speed and stability. Always validate your models on separate validation datasets to ensure that your optimization choices generalize well beyond the training data. Finally, embrace a mindset of continuous learning and adaptation. The landscape of deep learning is ever evolving, with new techniques and insights emerging regularly. Staying updated and being willing to experiment with different optimization strategies can keep your skills sharp and your models performing at their best. Beyond the basics of Adam and RMSprop, the field of adaptive optimization continues to evolve with advanced algorithms and techniques. Researchers are exploring new ways to integrate adaptive optimizers with neural architecture search, allowing for automated discovery of optimal network structures and hyperparameters. This integration can significantly enhance the efficiency and effectiveness of model training. Additionally, there is growing interest in understanding the impact of optimization choices on model interpretability. As models become more complex, ensuring that they remain interpretable is a critical challenge. Recent research has also focused on developing optimizers that can better handle non-convex optimization landscapes, which are common in deep learning. These advancements are paving the way for more robust and efficient training methods. Looking to the future, expect to see continued innovation in optimization algorithms, possibly incorporating elements of reinforcement learning and meta-learning to further improve adaptability and performance. Staying abreast of these trends and advancements can provide valuable insights and tools for deep learning practitioners seeking to push the boundaries of what's possible.
To illustrate the power of adaptive optimization, let's examine a real-world case study. Consider a natural language processing (NLP) application where the goal is to train a language model for sentiment analysis. Here, the Adam optimizer is used to efficiently handle the sparse gradients typical in NLP tasks. By dynamically adjusting the learning rates, Adam accelerates the convergence process, reducing training time while maintaining high accuracy. In another example, image recognition tasks benefit from the RMSprop optimizer, which stabilizes training by adapting to the rapidly changing gradients common in visual data. These optimizers not only enhance training efficiency but also simplify the process of hyperparameter tuning, allowing practitioners to focus more on model architecture and feature engineering. However, real-world applications also present challenges, such as dealing with large-scale datasets and ensuring model robustness. By carefully selecting and tuning adaptive optimizers, these challenges can be effectively managed. The lessons learned from these applications highlight the importance of understanding the specific requirements and characteristics of your task, as well as the potential for adaptive optimizers to drive performance improvements in diverse settings.
In conclusion, mastering adaptive optimization in PyTorch equips you with powerful tools to enhance your deep learning projects. We've explored the significance of adaptive optimizers like Adam and RMSprop, their implementation, and best practices for their use. Remember that experimentation and continuous learning are crucial in this ever-evolving field. Stay curious, and don't hesitate to explore new techniques and advancements. As you apply these insights to your work, you'll find that adaptive optimizers can significantly improve your model's performance and stability. Thank you for joining us on this journey, and we encourage you to continue exploring the fascinating world of deep learning optimization.